California. Gaurav got his bachelor's in computer science and engineering from IIT Bombay, and then he came to USC where he got his master's and PhD degrees, and subsequently he joined there, and he has done a lot of good work in multi-robot networks, and today he's going to be planning for them and decision making, and today he's going to be talking about their application to underwater vehicles. And for his work, he has won several awards. He's a fellow of IEEE. He's also got the Jnaneshwar Career Award. So, Gaurav, without further ado, we'll do.
All right. Thanks a lot, Nikhil. And so it's a pleasure to be here, and really nice to come out and visit. The last time I was here was when I was a grad student, maybe 15 years ago. I had this vague memory of a lot of red brick buildings, and now I have a firm recollection of the buildings I saw. I believe I didn't see this one because it probably didn't exist at the time. It's really nice to be here, and thanks for the invitation. So I changed the title of my talk a little bit from what I had made up and sent to Nikhil, but the theme is basically the theme of underwater sensing. So I'm a computer science person by training who does robotics, and I think about planning problems for robots. And particularly in the last half decade or so, I've been focusing on planning problems for underwater systems. And so you will see examples of data collected from underwater vehicles, and the talk will be largely about how to process those data. And to some extent, we'll say something about how these vehicles should be tasked. And so this is a picture of one of the vehicles we use. It's one of the underwater gliders that my lab runs on a regular basis in the Southern California bight just off the coast of LA. The data you're going to see today is going to come from some other vehicles, but that's my stock picture for advertising our lab's workforce vehicle. And so the theme today is to give you some sense of the kinds of problems we think about for planning, which have to do with sensing in the natural world. The idea that you can put robots out there as sentinels that make measurements about what is going on in the natural world is something that has a lot of currency today. And we have a remarkable facility for doing this with vehicles today, particularly in the water. We even have the ability to do this on other planets, somewhat surprisingly. Right? We put a robot out on Mars and actually take data using it. And to some extent, if you think of the satellites that we've built and other such devices, there have been a lot of robotic systems that have been used explicitly to make measurements. So the kinds of robots we care about are robots that either inspect big man-made systems like ships, but these systems are out in the natural world, so they can't be brought somewhere in where you can control the conditions under which you want to inspect them. Or we want to inspect the natural environment itself. So we want to learn something about large bodies of water. We want to track natural phenomena, things of this kind. So the measurements that we want to make need to be made sort of out there, if you will, right? And so my lab has worked on a variety of problems concerning these. And so there are some pictures here of many of the projects we've worked on, and I'll tell you a little bit about which ones I plan to focus on today. And so I've sort of divided these into two groups. On the right, there's a set of pictures having to do with detecting things in the natural world, reconstructing them, building maps of them, and then moving in the natural world to gather data from sites of high interest, if you will. And each of these has been a focus of activity in our lab. And we've largely pursued these in settings that thank you so much. I've chosen to call static for want of a better label. And what I really mean by static here is that we're going to move the vehicle around, but the thing we're trying to either detect or reconstruct or gather data from is moving very slowly or not moving at all. So for example, here, this icon shows a detection problem for looking at a sonar scan and picking out an object of interest, which is what the circle shows. Or a complicated propeller assembly that's sitting at the bottom of a ship in harbor and reconstructing its geometry. So these are examples sort of where the thing you care about isn't really moving, you want some fine detail. And you want to plan paths for your vehicle that reveal these details. Right? So that's sort of what I mean by static. In this context, there's some pre-assigned sites at the bottom of the ocean floor, and the job of the vehicle is to visit the right sites to get, in some sense, the maximum possible information out of this system. These kinds of detection problems are meant to illustrate certain problems we've pursued recently where we want to detect sort of hotspots of biological activity in the ocean. So the red spots here are chlorophyll hotspots. And these do move. They're not strictly static. They get pushed along. They predominantly advent because of the motion of the ocean. But there's also some ecology going on, so these things are growing as the system moves around. We want to build maps of such systems. Explicitly in the work on tracking, we're explicitly interested in things that move somewhat faster. We're interested in fast-moving algal blooms or bloom dynamics that are sort of split into different pieces, and we want to build maps of these. We have some limited work also in manipulating objects on the surface of the water, and then some work on persistent surveillance of bodies of water. So my focus today is really going to be on certain classes of detection problems and certain classes of reconstruction problems and one data gathering problem. And I'll invite you to sort of look at our papers on these, or if you call me back, I'll give you a whole different talk on some of these later. And so while our focus today is going to be on detection and on reconstruction, I just wanted to give you a one-slide overview of stuff I'm not going to talk about. We have some work on using ocean forecasts to do tracking of chlorophyll blooms in particular, of algal blooms in particular. This polygon is a bounding polygon of the bloom forecast, and the red and yellow trajectories are trajectories or plans for trajectories of two gliders, one of which is tracking the centroid of this bloom, and the other is tracking a boundary point of the bloom. And so we rely on control techniques developed here and elsewhere to control the low-level dynamics out of the vehicle, and we focus on tasking these vehicles in the form of an informative path plan. Where should they go next over a time scale of weeks and days and hours? We've done this in a couple of different ways. We've done this using ocean forecasts that our colleagues at JPL produced for us based on the ocean dynamics in the local coastal ocean. We've also done this by tagging features of interest in the ocean by putting drifters into those features with sort of long sails that float along with the water. And then we've done some Lagrangian tracking work where the vehicles of interest actually follow the drifter as it moves along. And so if you sit in the vehicle frame, you'll see the vehicles sort of orbit you, nominally executing this square orbit around you. And so the planning work for this is somewhat intricate because these vehicles get tasked in a global coordinate system attached to the Earth. As the drifter is moving around, you want the drifter to see the vehicle around it execute some sort of a stable orbit. So we have some work of this side. All of this was recently enacted in an experiment out in Mbari with collaborators at the Monterey Bay Aquarium Research Institute and a few others to bring together an assemblage of vehicles. And late last year, under the auspices of a big initiative at Mbari, we participated in a joint experiment where some of these tracking technologies were used. They are sort of an illustration. The video is meant to just show you an illustration of the kinds of ways in which these big experiments come together. There are many underwater vehicles playing here. There are 2 Mbari vehicles, and our techniques for doing this Lagrangian tracking are what are going to cause one of the vehicles to orbit the drifter that's in place here. It's a bit hard to tell from here, and I don't want to spend a lot of time narrating what's going on, but this is a replay of data from 2 days worth of experimental trials last October, where the tracks that you see moving around are vehicles, and the path plans generated for the orbiting vehicle are generated using some of our techniques. But I can tell you more about this offline. It's not the main focus of the talk today. So as I said, the focus of my talk today really will be this far right corner. I'll tell you a little bit about detection, reconstruction, and data gathering. So primarily we work in this part of the world. When I got into robotics, I realized that oceanography is in many ways a local enterprise. You make friends with a local oceanographer, and they care passionately about a little piece of the ocean. Even though I learned technically that there's no such thing as many oceans, there's only the world's ocean. But the ocean we care about is this little patch of ocean. To somebody trained in computer science and who had primarily only worked with robots in the lab, this is a dauntingly big piece of water. To an oceanographer, this is a small patch of ocean. So we are talking about 50-odd kilometers this way and about 100-odd kilometers up and down the Southern California Bight. We are sitting here in Los Angeles. We have a marine lab on the Catalina Island, which is sitting about right here. So very often we'll stage either from the port of LA or Long Beach or from the marine lab out here, and most of our experimental work is done here. And what we've done, myself and the groups of Bert Jones, who's an oceanographer, and Dave Caron's group, who's a marine microbiologist, is we've sort of wired up this piece of ocean. So we have 10 high-frequency radar sites up and down this coast at about 30 kilometer intervals. These do surface wave velocity measurements of the light. They get fed into an ocean model that our colleagues at JPL run and operate, which generates forecasts for us for what this patch of ocean is likely to do. These forecasts are quite intricate, and they're done really nicely, and really for us, they serve as an amazing prior, if you will, for doing vehicle planning. So we at least have some sense of what the local current distribution is going to look like. We also have some smaller vehicles that we use for in-harbor work. We have some profilers that sit on a couple of oil rigs that are out in the Bight, and we've sort of tried to piggyback on a lot of other infrastructure that people have put out. And we operate 3 gliders in this area. So this is roughly where we've been operating. So as I said, we have 2 pieces today. The first piece I'll tell you a little bit about is gathering data from an underwater sensor network. We have colleagues at the USGS who have placed just off the coast of LA on the San Andreas Fault a set of seismic nodes at the ocean bottom. The local Southern California Bight goes down to approximately 1 kilometer in depth at its deepest point. Our vehicles are rated typically to 1 kilometer depth. We have never really operated them at that depth. We've generally always operated them in the upper column of the water. Notionally, we can go down to 1 kilometer. And so the challenge here is going to be to plan tours to visit the right sites here to get information from these sites. Seismic people care about this a lot because very often they discover to their dismay that they will put down their their geophones, and then when they come back a few months later, they notice the logger stopped logging weeks ago or months ago. And there's not a continuous communication channel to the surface from these once they're in place at the ocean bottom. And I'll tell you a little bit about this classification and surface inspection work, which is done in collaboration with some folks at MIT. So, as I said, these underwater sensor networks, they're sort of in place to monitor environmental conditions, seismic activity, and the like. And they have some low bandwidth acoustic communication capabilities. They need to conserve power, so they can't continually send data up to the surface, but they can occasionally do a data dump, particularly if a vehicle happens to come nearby. And so the energetics of acoustics are such that you get significant decay over long distances. So if a vehicle can come close enough, then with relatively low power, one can transmit to the vehicle. You can essentially data mule the data off these things. Send the vehicle out, grab some data, send it to the next sensor, grab some data. And so the question we're trying to ask somewhat more formally will be, what are the right sites to go to? In some sense, can you design tours for these vehicles that are in some sense maximally informative? Clearly the answer is going to depend a lot on what you mean by informative and how you define the appropriate cost function. And so we'll show some optimizations for particular cost functions. And the challenge really here is how do you plan a high quality and yet somehow a low cost path for your vehicle. And I'm going to make the claim that if you have better acoustic communication models for the underwater communication, then in fact this can inform the techniques you use for path planning. So there's a somewhat tighter interplay between these than people have noticed in the past. And that's this work is about 9 months old, so this is my test drive this year to try and get people to believe this. It's not clear that everybody believes this, but I'm going to try and believe this. It's very important to note that my abstraction for the underwater vehicle here is such that somebody, like Derek, for example, has figured out how to do the control for these vehicles, right? So the vehicle dynamics are understood and modeled at some level, right? And somebody's wrapped a controller around these, right? A steering controller, a heading controller, whatever is the appropriate thing, right? And that this mechanism is understood well enough that it presents an abstraction to someone like me that allows me to say, go to X, Y, Z. This may or may not be an appropriate abstraction for every known vehicle, right? It's not clear that you can do this, but for many classes of vehicles, there's been a decade or so of work in really trying to understand their dynamics and to, in some sense, be able to control out, if you will, the known dynamics of the vehicle. And so this work rests on that, right? So there's, of course, a lot of related work in underwater acoustic communication and on the appropriate kinds of planning problems. In fact, there's been a lot of work on data muling from sensor networks, particularly from Volkan Isu's group in Minnesota recently. much of that has not realized, in fact, all of that has not depended on models of communication. Typically, for many of these kinds of problems, the assumption is that the communication model is either perfect or not at all. So you communicate with nodes when you're close enough, and there's no loss when you do so, and when you're outside a certain distance, then there's no communication. So this is sort of a unit disk model of communication. We'll relax that here. And then there's some work on network data collection from Daniela's group recently, which is relied primarily on infrared-based communication underwater, which has entirely different characteristics than the kind of acoustic that we're thinking about. Right? All right, so here's one cut at the statement of the problem. There's some sort of a sensor field, and the task of the vehicle is to visit the appropriate set of sensors to get some information out. Right? We're going to define some notion of information quality, which will denote by the function I, of a set of sensors Y. So given a set of sensors Y, we will have some function that will tell us what the information quality is, and I can speak a little bit later about what are appropriate measures of information quality. And all we ask at the present is that this function I be additive. Right? So in other words, if you take two sets and if you gather information from them and they're disjoint, then the sum of the information is the sum of the individual sets. We'll assign some metric to the traversal cost C of going from sensor xi to sensor xj. And for purposes of this work, this cost is going to be the Euclidean distance between the two sensors. This is something that's worth revisiting, and because this is our first cut at the problem, this is not a mature assumption. Underwater, for example, in presence of currents, it is completely not the case that you have metrics of this type. Right? So this is a simplification. It's worth noting. And we'll assume that there's some measure of communication quality, a probabilistic measure of packets going from sensor xn to the vehicle. And this communication quality measure obviously is going to depend on the acoustic model that we have. And it's going to be distance dependent, it's going to depend on a couple of other things. So given this notation, one can write a quantity, which is the received information quality, along a particular path that the vehicle takes. Right? And this is relatively easy to write with an independence assumption between the various sets of sensors that you visit. So the assumption is that the information that you get from set Y1 and the information that you get from set Y2, as long as there's no overlap between Y1 and Y2, then there's no information overlap between these two, so you can in fact multiply the problem. So given this measure, one can define an optimization problem. And the optimization problem says, find me the path P star that minimizes the total cost of traverse such that the received information is above some threshold. And I'll take tau as some sort of a design parameter, and I'll say I need the following amount of information in the appropriate units. And then given my cost model, I want the path that actually minimizes this cost. So now there are variants of this problem where we've made a simplifying assumption on cost, but we will not make a similar simplifying assumption on the one. So there are variants where the communication model is on-off. So you say, look, if you're within a certain distance, you get all the packets. If you're not, you don't get any. But we can do a little bit better than this. And by we, I mean my collaborator, Urbashi Mitra, who works with us on this project. We have the ability to estimate the probability of packet success as a function of distance. And we can do this from data. We can do this from underwater data gathered from a vehicle. I'll show you that in a second. So what you can do is you can model this in two parts. What you really want to arrive at is some sort of packet error rate. And the packet error rate accommodates two kinds of disturbances. You accommodate certain, if you will, fluctuations which are intended to hide the fact that you don't know the parametric distribution, which are modeled as some sort of Gaussian random fluctuations on a log normal distribution. And then a noise model which is intended to model sort of all the other stuff that's happening in the water. Mostly turbulence and thermal noise. There's also some impact of shipping activity. And so what we really want to end up with is, given the distance from the sensor to the vehicle, we want to end up with some sort of contours that give us the probability of packet success. And we want this to encode not just the distance, but also the particular modulation used for doing the communication. So we want to get a little bit deeper into whether the acoustic comms is TDMA, it's time division multiple access, or code division or so on. So we want to dig a little bit deeper into the protocol stack to sort of see if there's some impact. And actually the secret hope is that when we solve optimization problems of this kind, we can turn it around and tell an acoustic comms person that you really shouldn't be doing TDMA, you should be doing random access, for example. Or given a cost measure, there's no point in spending the effort you're spending on doing comms in a certain way, right? That's the arrogant hope. We'll see if that plays out. That's also to be TBD at this point. So anyway, so the way this acoustic model that I'll show you in a second was built was from data gathered off of the Lucille. This was data generously provided to us from the Woods Hole Oceanographic Institution from Hanu Singh's group. This is a collaborator on one of our ONR Muri's. This data were collected just off of Northern California, and you can see some details here. But roughly speaking, the vehicle hovers a few meters off the seafloor. It's sitting in about 120 to 130 meters of water. There's a surface vessel that's sitting at the surface. Packets are transmitted from the vehicle to the surface, and there's an acknowledgement sent back. Over thousands of packets, we gathered the statistics of these packets and built the model using these. The channel depth just off the coast of LA where we're operating is actually significantly different. So there's some concern that we don't quite have the right parameters for the problem we're solving for the channel we have. We haven't quite been able to acoustically characterize the channel there, so there's a gap there. But I'm going to show you algorithmic results that don't necessarily depend on the exact numbers, but it's important to note that model fitting needs to happen fairly carefully depending on what regime you're operating.
These locations are quite discrete, so there's no...
Yeah. No, there is, because depending on shelves and depending on where the vehicle sits relative to the surface, you get all kinds of different multi-path geometries. And so just because we characterize the channel that was sitting off of the northern San Andreas doesn't really mean we characterize the acoustic channel very well where we are sitting. So I don't want to make the claim that we have a good model of the channel we are there. We happen to have that data, so we used it to instantiate a model. And so the model fit looks like this. There's a log normal random variable that models the gain, and then there's a normal distribution about it, and then there's some noise factors associated with the terms that we essentially don't model. And from this, it's possible to derive a packet error rate. The packet error rate, which is this quantity we care about in the end, this is done by a particular kind of modulation, which is not very important for this talk. This is BPSK modulation. And the important thing about the packet error rate is that it's possible to incorporate the rate at which packets are sent R, and also the number of blocks in each packet B. So it's possible to go from this PB, which is a bit error rate, very commonly used to model loss, to a full packet error rate, which accommodates how fast you're sending packets and how you do the blocking in this particular protocol that you're using. So in the previous slide, when I said it's our hope to dig a little bit deeper into protocol stack, this is what we mean. So given a particular way of modulating bits into packets, we can incorporate that into the noise model for the communication. The advantage of doing this is that later it's possible to do a sensitivity analysis to these kinds of parameters. So you can expose them to the path planning problem itself, right? So the idea is to dig a little bit deeper into the path planning optimization and look at the impacts of making certain choices in the acoustic communication model, right? To an acoustic communications person, and if there is one here, this is sort of acoustic communications 101. There's nothing sophisticated happening from an acoustic comms point of view. The entire point is, can we exploit some basic insights from there and A, do better planning, and B, say something about how you design comms. Okay, so what we get out of this communication model are these probabilistic neighborhoods, and they depend on the modulation. They depend on the distance, of course, but they also depend on the modulation scheme, right? And what these probabilistic, these neighborhoods do for us is basically we can say, well, what is the packet error rate that you want to tolerate? So if you want to tolerate an 80% packet error rate, then you can essentially look at this model and say it happens at this distance. At least in the isotropic case, there's one distance. The more sophisticated models are not isotropic. So what you could do is you could say, look, if you want to do planning and you want to hit certain packet error rates, then the right thing to do, given that there's uncertainty in where the vehicle ends up when you command it to go to a certain location, you should think of this as some sort of a markup decision process problem, where you say, look, if the vehicle ends up at a certain location, the right thing to do is to understand that when you command a certain location, you're not going to end up exactly there. So rather than learn what is the next best place to go to, you should learn this for all possible locations. You should learn a policy instead of just a plan. So a plan says, go here, then go here, then go here, and then go here, and you're done. A policy says, I'll tell you what the next best place to go to is irrespective of where you end up. Right? And that would be the most general thing that a planning person would learn. Right? Both would require, of course, an underlying control technique. A policy is more forgiving to a control technique that doesn't, in fact, put you where you need to be at the end. For any reasonable size problem, learning a policy ends up being, or computing a policy ends up being difficult. One generally can't do it, right? So what one does is, instead of looking at all the possible locations you want to go to, you ask whether one can do this in some way by in fact exploiting the fact that you have high likelihood of getting packets without actually visiting the sensor, right? So if you come near enough, you have a high likelihood of getting packets from the sensor. So in a probabilistic sense, if you want high payoff, then really the problem is not visiting sensors, but the problem is visiting neighborhoods of sensors. And so the correct way to think about this is to think about visiting neighborhoods that then somehow maximally cover the sensors you have. And so rather than think about going to sensor A and then sensor B, I ask the question, what's a circle I want to visit, and to what degree do I want to visit it? How far do I want to penetrate into it? So in somehow I get a quick peek at the most number of sensors. It's not quite the most number of sensors, it's the most informative view is what I want, right?
All the sensors have equal value?
Yeah, so here they all have equal value, right? There's a weighting term that I'll introduce, but we've set it to 1. So clearly the cost function would bias these in some way. For example, the quality of the signal or the ones you visited in the last tour, obviously it could be maybe no-nos, or just intrinsically to the seismologist, some are more important than others. You can think of many things that make it different. And that they would bias the tour. In reality, I think none of our geology friends will let the vehicle just do this based on the plan. I mean, they could exert a strong influence on what the vehicle will do. So what we want really is, in some sense, to model this using some framework that ignores neighborhoods with high cost and low information, right? Not ignore, but probabilistically weight them less, right? And so we're going to plan using some version of the traveling salesperson problem, but we're going to do it in neighborhoods. We're not going to do it on sites, right? And we're going to do this in some price collecting fashion. So the price collecting variant of the traveling salesperson problem says, you don't have to visit all nodes. You get a prize when you visit a node, and you should just maximize the amount of prize you get, right? And that means leaving some nodes out, that's okay, because there's a cost to visiting nodes. And so rather than TSP, which says visit all nodes and give me the minimal cost tour, the price collecting TSP says maximize the prize you collect given a cost model. And if the maximal price given the cost ends up meaning you leave some nodes out, then that's fine. The correct answer is which nodes to leave out. So that's the variant we use. We'll use it on neighborhoods. Okay, so the question now is how you generate a tour that hits all neighborhoods. We don't want to do this. This is standard TSP. This is not optimal, right? What we really want somehow is to figure out which are these circles. And so what you want to do is you want to somehow enter one of these circles, and then you want to find the right drop-off point so that you can enter one of these other circles, right? And then, so the question is, which are these right circles? What radii do you pick for them, right? And what's the kind of covering property you want for these circles, right? So the kind of covering property we look for is this maximal independent set property, right? And we're going to do this we're going to do one variant of this, which actually fixes the radii of these circles. So we're not going to ask these two questions independently. We're going to pick a probabilistic threshold because the radius of this circle from the center tells you what packet error rate you're willing to tolerate. So we're going to pick a number. We're going to pick 80% and say that defines circles of a certain size from any given sensor. Then we're going to ask, where do you want to put these circles so that in some sense you maximally cover all the sensors you have. And then we'll ask the question, what order do you want to visit them in, and what costs. There's no uncertainty in sensor position. It's a very good question. None, right? So there's no model for it here. The assumption is you know exactly where. That, it turns out, is not a very bad assumption for the seismic work because they are surveyed and placed, and they're in fact embedded on the seafloor bottom, so they're actually quite good. Doesn't work for other things, of course. Yeah.
So in the actual practical application, what is that 80% distance compared to the distance between sensors?
It's much smaller than the distance between sensors, an order of magnitude or less. Yeah. 2 orders of magnitude, significantly smaller. So the entire seismic array that our collaborators at the USGS have is approximately 150 kilometers wide. The internode distance is approximately, the closest nodes are no less than 2 kilometers together. P equal to 80% translates to 200 meters, 300 meters. They have extremely small acoustic transponders on that. They're also directional, which we don't model here, so there's some subtleties that are lost.
How does the vehicle know where it is?
Yeah, so that's a very good question. Our vehicles only know where they are accurately when they surface, when they get a GPS fix. They dead reckon underwater. And this is where we get to say that there are people who know how to control vehicles and can tell us where the vehicle is and can do trajectory tracking for us. There's a drift in the vehicle underwater, and these drifts are fairly large. For our glider vehicles, over dives that go a few kilometers, we can be off by as much as half a kilometer to a kilometer when we surface. And those numbers are somewhat disconcertingly high because if two numbers are 2 kilometers apart and you aim for one versus the other, it's possible to get it completely wrong.
Do you have a unique signature with each of these sensors?
Yeah, they all have unique signatures. It helps us to localize, so clearly, when we build this out as a system, there's more engineering that needs to happen. We have now, if we abstract away sort of localization, we know how to design the tours, but we wouldn't be able to just implement it the way it's supposed to right now. Ideally, it's been suggested that what we really need to be doing is some sort of active localization with these as beacons, and then really do sort of underwater localization with them. And of course, there are groups who do underwater localization for a living, so we would likely use some of the techniques to do that. All right, so let me just show you the results. I'm running a little bit late, so it turns out there's a known result for deterministic neighborhoods and full data collection, which is in the literature. It goes back about 8 years. And this is a version of the problem that says, given deterministic neighborhoods around sensors that are pre-designed, and you want to visit and you want to gather data from every sensor, then it turns out that there's an approximation algorithm to the problem. TSP is NP-complete, so you need either to exhaustively look through it, which you can only do for small problems, or you need some sort of approximation algorithm. And it turns out there is an approximation algorithm, and the guarantee that it gives is that the approximation algorithm will produce a path that is guaranteed to be this constant factor or less times the optimal path, right? So this is approximately 12 times 1 times something, so this is approximately 13 or 14. So this approximation guarantee, it may strike you as not particularly great, that it's the path this computes is no worse than 15 times the length of the optimal path. As is the way with many of these techniques, the proof technique is what limits this statement. If you run this technique on deterministic neighborhoods and full collection, in practice, the paths you get for real problems tend to be surprisingly close to the optimal path. Right? Now, of course, we can only run them for ones where we can compute the optimal path, so these are small problems. How this grows with size of problem is an open problem, right? So that is not known, but in any case, that is true. Our first paper in the area extends this to the price collecting case, where instead of collecting data from all sensors, we basically allow the system to skip sensors and instead just try to maximize the total price collector. And we can show that a very, very similar bound, in fact, just a constant factor off from this, exists using very similar proof techniques to this. And we can also show that the quality of the approximate path is bounded relative to the optimal path. So this paper just appeared, and there's a somewhat more sophisticated version of it appearing. So let me just sort of show you the intuition. So it turns out that the proof relies first on proving what you can get as the approximation bound for disks that don't overlap. And then the transition to overlapping disks is not complicated from there. The price collecting problem really enforces, one can get exactly the same bound, but there's one constraint associated with it. And the constraint is on the nature of the price you collect at each node. And that has a particular structure, which is the only intuition I want you to keep in your mind. This is the price collected at node I, and in our proof, this price has to be greater than or equal to twice the diameter of one of these neighborhood circles. So in other words, it's not possible for these maximally independent set circles to overlap. Given that assumption, we can show that we get essentially the same bound, right? And experimentally that seems fine because the scale factors involved are such that these prizes don't need to be very small. But that's the only thing I want you to keep in mind. The proof is not particularly novel. It's really essentially the same structure as what's in the literature, but we can extend it to this sort of price collecting case. This is good for us because now essentially what we can do is we don't need deterministic neighborhoods. And as long as we allow a price structure which has this lower bound, we can essentially pick any price structure above that. And we can essentially get a guarantee that our paths that we're computing are good in some sense, right? And so, so yeah, I mean, you don't want to do this, visiting sensors. This one, there's already sort of a formal analysis. What we do is this, effectively, right? What we're doing is, right now, is we're generating these maximally independent sets, and we're visiting the centers of this covering set. And we've been able to show that the bound not only works in 2D, works for non-deterministic neighborhoods with this constraint on price, it also extends to 3D. So we can do this for spheres, which is somewhat more complicated geometry and involves sphere packing and so on. So I'm glossing over the details of the proof, but if you're interested, we can do some of these things. So those are some of the sort of the nice things we've been able to show. What it looks like in practice is what you might imagine it looks like. So there's a data collection run. This is a simulation where the sensor field was drawn from actual placements, but the vehicle is sort of idealized, and I'm just sort of showing you what happens. And so you get tours that, well, they look like tours, as you might expect in a QSP, right? If you do this in the case where there's a price collecting variant, then some sensors will get skipped, and you can see the algorithm figures out what are the right ones to skip. It's not possible to develop any intuition from looking at this. I'm just sort of showing you that this is what a typical output looks like, what a planned tour looks like.
In each run, for example, you could have database collected multiple dimensions in the same sensor.
No. So the way this works is when you're in a neighborhood, you collect data from all the sensors that are within the peak threshold of that neighborhood, and then not again. So there's a guarantee that there's no revisit. There's a no revisit guarantee. So you can trivially show that a revisiting variant of this can be eliminated and will never happen because, yeah, so this is not hard to show. I mean, you can always shortcut paths that cause revisiting to get a better technique. And so this is, I think, shown on, this is the first rollout of the seismic array just off of the San Andreas. So this is about I think it's about 100 kilometers by 100 kilometers, so roughly like that. It's interesting, the exact locations of the underwater sensors that we use are not to be made public for reasons I don't fully understand. So our collaborators told us not to include GPS coordinates on any of these. I'm a little surprised, but I don't know how it works in seismology, but that's the thing. Here's some data on how this works in a variety of settings. So you'll see 3 curves on each one. On the picture on the left is full data collection, where the vehicle is required to gather data from all sensors. On the right is the price collecting variant. On the y-axis, I think, is essentially the time it takes to do the tour. And here you'll see the average cost on here. The cost is how much data you gather plus the penalty you incur for leaving things out. And on the x-axis, you see the transmission power. The takeaway message from this is the blue variant is the proposed algorithm, which is this sort of price collecting PSP variant on probabilistic contours for which we have the theoretical result on the covering set. And you can see that in terms of transmission power, if you compare the completion time, you need less power. Or if you compare how much payoff you get in terms of information, you can do it for less power compared to, so the dummy method, of course, is just move to the nearest closest sensor, which doesn't do as well. But even if you just ignore contours and don't do neighborhoods and run a TCP, we can beat that. And the point is that if you do full data collection, then really our technique doesn't do a whole lot better, right? I mean, the yellow and blue lines are not separated by much. It's really the case where, in fact, you're allowed to leave some nodes out, and you only insist on gathering a certain amount of information and not get hung up on visiting all sensors, is where you can see that we do better, right? That's the case we care about. So insofar as you really intend doing some maximal information gathering, this is a useful technique. So what does that mean? I mean, why did we care about this? Seems a little contrived, right? So the reason is as follows. The way there are 2 modes in which these underwater arrays are used, right? One mode is where, of course, they want the data from all these loggers in the end. There's no, excuse me, there's no getting away from that. But the immediacy is to detect patterns from this data. Right? What you really want to know is whether, as an aggregate, this set of sensors is telling you something. If it's possible to get all data from them at all times, people like me are redundant. No seismologist needs me, right? Insofar as that's not possible, there are two needs. One is, I'll wait 6 months to get all the data, but can you tell me something about a developing pattern today? These developing patterns don't necessarily need data from all sensors. That's the price collecting variant we're aiming for, is can you give me a signature that is informative, right? And so notice, I haven't told you what I is. I said assume a cost function I, right? Assume some information gain I. We used information here. We use mutual information here. But our real interest is in trying to capture I functions that are meaningful to the particular sort of domain. And that's our niche, basically, right? In the end, over a long time scale, you made all the data out, you're gonna mine it later, you're gonna look, but the immediate need is patterns, right? And so that's this variant where we hope to make a difference. Where random probes will not give you the pattern, that's the right line. Where visiting all sensors will not give you the right thing, which you pay too high a cost, where our technique will hopefully pay off. So that's our initial thought. We've not applied this to the actual sensor set, right? We've used their locations to plan the surveys, but we haven't actually gotten any data off of it yet. So we don't have good designs for these functions yet. So we're sort of in the stage where we have an algorithm, but we haven't done the full thing yet. So halfway there, everything.
You have onboard processing on your robot?
We have a limited amount of onboard processing. These lighter vehicles come with a legacy, really annoying old computer, which we retrofitted with a small dumpster running business. So we do some onboard processing. We don't have a tremendous need to do onboard processing because these sensor fields don't change. So the plan is generated sort of at mission time, and then the vehicle executes the plan. Now, the question you're getting at, of course, is as the pattern develops, should you not be changing the plan? That's well beyond our ability right now. I mean, we haven't even developed any sort of underlying formulation for it. Presumably people would like that at some point. But we are really in data gathering mode here. We are really not in reacting mode.
I was thinking of like mind theory.
Yeah,
Don't
yeah,
know where the minds
yeah.
are.
I'll show you an example in a second of that. But even there, we are a little shy of doing exactly what you're saying. You're right. There's a decision problem. We are framing this as a one-shot decision problem. You make the decision, you do your thing. Clearly, that's not the whole story. There's more to it. So now there's a couple of variants of this, right? So you don't have to communicate with one sensor at a time. You can communicate with multiple sensors at a time, particularly if you slice the acoustic channel up in interesting ways. And so we have variants of this that extend not just to simple protocols, but you can do this in a couple of different ways. You can model the common information from multiple sensors. So if you have two sensor sets, ZI and ZJ, you can model the common information by some sort of conditional mutual information term. And we can also have a entropy term that models how much innovation there is when you add a new set of sensors, when you listen to a new set of sensors. And then we can define some sort of correlation model. In our current thinking, these correlations are pairwise. They're limited to two sensors at a time, and they fall off exponentially with distance. So nearby sensors are highly correlated, faraway ones are not, which is not bad assumption. And we can do things where we can now get a little bit deeper in this protocol. I'll just skip over this in the interest of moving to my next piece. But instead of just looking at packetizing rates, we can actually get into how the acoustic channel is sliced. We can involve those parameters. And the reason to do it is because we can then turn the problem around. So the only thing I wanted to show you was the payoff from this is one can now ask the other question, which is one can say, look, if you decided to use time division multiple access versus random access for your acoustic channel, then what's the impact on the kinds of information gain you expect to get from the optimal tool you want? Right? And so how many transmission rounds versus how much information gain? And you can see that if you're running TDMA with large neighborhoods, you sort of get this. Sorry, you get the middle one here, whereas TDMA with small neighborhoods, you get this. So the question that was asked earlier is, how big are these neighborhoods relative to what you're doing? If you know that, and in our problem, that's something that's known in advance, then our hope is to convince our acoustic comms colleagues to change the modulation based on some of these numbers. So we have some design curves now. So we have some ROC curves basically sort of push back on the acoustic comms people and say, hey, you should be redesigning the way you're thinking about this. All of this is done under some assumptions right now, right? So there's very particular cost models, there's very particular payoff model, there's very particular model of the dependence between the information gain you expect from the adjacent sensors. So there's a lot of room here to relax this. And I don't want to claim that we understand how to do all of this, but my claim for this first part is that we hope we've opened a window into something a little bit tighter than what people have conventionally done with underwater comms and tactical. So we don't know which of these is high payoff. These distinctions I'm making on this picture may not be the right distinctions. It's very important when you begin to sort of appreciate that. So they may not be. They look nice, and they're in multiple colors, and the curves are nicely separated. But that doesn't necessarily mean that they're as significant, right? So I don't want to make that claim. I just want to make the claim that there's maybe an opening here to figure out what the right parameter choices are. And so we're going to push on this a bit in the coming year to see if we can really impact the way this is done for vehicles. And then, of course, we have a deployment plan coming up later in the year where we're going to try and do sort of an instance of the problem. There are many protocol comparisons. I'll skip through the details. They're not. So,
Just one question for you.
yeah.
The spatial distribution of these sensors, we
Yeah.
obviously are.
Yeah.
So how long does it take, and how critical is that in terms of actually getting the data, and how quick to gain the data in terms of?
Well, I mean, the wrong way to ask any person in the natural sciences is how quickly, because the answer is now. So that's not an option. But you know, they would like these slow-moving glider vehicles. This survey is slow because they're moving, you know, kilometer an hour is pretty good pace, right? So you're not going to go 200 kilometers. I mean, you can, but it's going to take you a long, long time, right? So the thought is to do this with a fleet of vehicles, to chop the problem up into smaller problems, right? And do this in parallel. And also, it's not clear that our vehicles are the right vehicles to do this. I mean, I happen to have gliders in my lab, so that's what we test on. But in practice, it's not clear that that's the right vehicle. We probably need something that's a lot faster. Because most seismologists would expect a survey of this type. The excitement on these surveys is there's been some shore activity measured from an onshore network. What is this sea floor network saying? But tell me today, right? So if there's major aftershock happening, I want to know today, right? I don't want to know. So I suspect people are willing to wait a day, they're willing to wait 2 days, but they're not willing to wait a week and a half for your survey to complete. Right?
That was a good question.
And on land, I mean, they're just explicitly wired, or they have very nice, RF communication to all the boxes. So the fault is pretty well wired up and down the coast of California inland, but offshore it's a problem. This is also, some of these surveys will complement sort of these Neptune arrays and other sort of sea floor cabling that is now happening. So these will, vehicles are one way of getting data out, but people have suggested that, look, the right thing to do is to stretch a cable across the fault, and that's already happening. There's an extensive outlay for some of the East Coast as well. So this will fit, hopefully, in some bigger picture. So I still have maybe 2 minutes, or should I try to wrap up? I'm showing I've been speaking for 46 minutes.
Yes, you have 10 minutes.
Should I take 10 minutes? Is that okay? All right. So let me tell you a little bit about part 2, which is this classification and surface inspection stuff. I'll zip through it. So here the problem is different. So switch gears, right? So this is an inspection problem, but I'll tell you why this is also a planning problem for me, right? So what we want to do is we want to do these kinds of things. There's underwater surfaces, right? Ship hulls, ocean bottom, oil platforms, you name it, right? Some are part of the built environment, some are not. And we want to be able to model them, we want to be able to detect changes in them, right? So the mine problem is fits in this category. Somebody sneaks up to you and changes you have a model of what the underside of the ship should look like. Somebody's in place something on it. Now there's a change, right? Finally the change, you don't have a lot of time. It's not an option to take the ship into the dry dock. Run a vehicle around a big hull and tell me where the change is. Right? That kind of motivation. Okay, so here's the only quiz question of the talk. So here's a bunch of imaging sonar scans, right? So for some of you, I know you work in MRI, you work with sonar, you're used to seeing grainy pictures. So the question is, which of these imaging sonar scans contains an explosive device placed on a ship's hull? It's not clear that is the ship, by the way. And so we're sitting under the water line. In fact, the vehicle is here in the water. If you can see it, there's a pink yellow signature, right? And so this is data from Franz Huber at MIT. using his hovering AUV. And so, which of these contains the explosive device? Some of you are probably better than others at seeing it. I could never answer this question. The second one is the answer. So the answer is they all have it. Right? But the point is that it's easier to see from some views, which you all saw, right? This is the guy that stands out. But the point is all the views have it, right? And so people like me see path planning problems everywhere. The question I'm going to ask is, what are the right views? You got a vehicle, you got a limited amount of time. Where should you go next so that you maximally gain the most information about the likelihood of seeing something? Something known in that case, right? This is going to be a known signature, right? And so we're going to frame this as a problem of view selection, right? Okay. And so let me skip over this. So the problem we want to look at, it has a couple of different flavors. I'll give you sort of one variant of it, which is this active classification problem. How do you choose a path of viewing locations that best classifies the object? Okay. So define some generative object class H that generates a set of features. These features could be corners, they could be visual features based on your favorite vision techniques to do low-level extraction. And then there's some set of locations in the world. All features can't be observed from all locations. So for example, F1 and F2 are observable only from location 1, etc. Right? So there's some map like this, right? And so now the question we want to ask is given a number of classes and given features that distinguish these classes and given some mapping from locations to features, we can define this posterior probability. We can define this posterior probability of a particular class, right? And this is under an independence assumption, a conditional independence assumption of the features. So the assumption is that corner A and corner B, if they can be viewed from different locations, there's no conditional dependence on the probability of seeing this corner from location A on the probability of seeing the other corner from location B. That's easy. So under this assumption, one can now pose my favorite kind of problem. As you can see, there's a bit of a theme here, right? So given this, one can define some sort of a loss and a path cost, i.e. to go from location 1 to location 2, the vehicle pays a price, right? And so now one can define some sort of a, in expectation, one can actually define a cost. And one can ask for this optimal policy. And this optimal policy is essentially a path plan. The path plan is the minimum cost path such that this loss function is bounded. Okay, so you pick me a bound, and I'll tell you how close I can get to that bound and get the best, get sort of the lowest cost path. You can also frame this in the complementary way. Right? You can essentially ask for the path that minimizes this loss function such that the cost is less than some bound. This is complementary. So they lead to slightly different formulations. Right, and so the idea is that if you do active view selection, then you can reduce path cost, right? So if you actively decide where to go, then you can keep the path cost down and keep the payoff high, right? And so this is a variant of adaptive planning or sequential data gathering type problem. You can see that given an object, there may be sort of vantage points that are, high, low, medium. So the question is how you rank order these and design a technique that captures these. Right? And the advantage, of course, of adaptive path planning is that essentially you get what you want to define is some sort of splitting on features, right? So you have all the features. You want to ask which feature causes me to most quickly disambiguate between the hypotheses, right? And so if you do this right, then essentially in log of the number of features, you ought to be able to get to the hypothesis you care about. So that's sort of the payoff, as opposed to something purely sequential, where potentially you could visit all vantage points. And so this has been known for a while, and it turns out that there's some older work by Andreas Krause that actually shows that the greedy policy with information gain as your metric, you can show that for non-adaptive techniques, there's a plan that you can generate where the cost is a constant factor off from the optimal cost. And this is a result due to Andreas and Carlos going back about 6 years, right? It turns out also that there are other heuristics like edge cutting, which have a slightly different notion of the cost. So this cost needs to be submodular. If you're adaptive submodular, you can do more intricate things about it. So there are some known results about this on how to approach this. What we've been able to do is we've been able to take the adaptive submodular work and show that for variants of information gain suitable for the kinds of underwater inspection tasks we want to do, we can prove that those are also adaptive, submodular, and monotone. And we've been able to more or less directly apply their bounds. There's some modifications needed, and there's some technical details which are in the accompanying paper, but we're able to show that we can exploit some of these results. And so we can solve problems like this. So which viewing angles best identify the device? We can in fact show that we have this sort of good results. And in the interest of time, let me just show you the results. So here's the hull inspection set of results. So here's the raw data, and here's the hand-labeled data, where the explosive is in the red box, right? And we need this so that we have some ground truthing, right? So somebody stared at the data and told us where the object is, right? Now we can build a viewing model, and we can ask which views best reveal the object, and then we can actually test whether it's actually true, right? So there's some amount of synthetic metadata that needs to be created to actually do the testing. And it turns out if you look at the results, here they are. So on the y-axis you see the number of correct pixels identified as belonging to the object of interest, and on the x-axis you see the number of views. You'll see our technique here on top, sort of the information gain technique, which very rapidly identifies the correct number of pixels. Right? This is a small object with very few pixels. And you can see the difference between two viewing locations. This is the viewing location you all liked, and you could see the expected gain is the appropriate units is high. This is a viewing location that none of you liked in my original motivation. The expected gain is very low, right? And so effectively we can show that we can pick vantage points that minimize the cost, yet maximize the expected gain. And if you do things like random views, you get something that's not. It's not hard to design anything that's monotonic in these problems, right? So it's important to note that all of these planning problems, they're only interesting because there's cost, right? If making measurements was cost-free, then there is no science to these at all, right? You just visit all the locations, right? So either you need to pay a hefty price to go somewhere, or there's a timeliness constraint. But without the constraint, this is not the only reason it's an optimization problem, of course, is because there's something to optimize with the constraint. And even getting decent behavior that ramps up is not hard, because the first view you make always gives you some information. And so in problems of this kind, which are submodular, it's only the succeeding views that add less to to sort of the aggregate information, right? And so the challenge is how do you design trajectories that at each viewpoint do the next best thing, right? It's in many ways an old idea. This next best view problem has sort of been known in computer vision for a long time, so we're revisiting it in this new guise. All right. So what I'll do is, in the interest of time, I'll just leave the second piece of this out, and I'll stop in case there are questions. Let me just bring up my last slide. I was telling Jaydev this morning that I was fiddling with it till the end, and I thought I would squeeze one more thing in, but I'm not going to do that. So I'll stop here. So I told you a little bit about this here and this. I didn't quite get to mesh reconstruction. We'll save that for some other time. If you want to know more, there's stuff on our website about a bunch of other problems. Particularly the tracking problems, we have a set of work on where we interact with ocean models. What you didn't see here is any interaction with ocean models, right? So somehow the medium has been abstracted away in these problems. That's about half our work. The remaining stuff we actually care quite a bit about how the water is pushing the vehicles around. So you can learn more about it there. And I should point out that the work here is really the work of two postdocs, Geoff Hollinger and Ryan Smith. And JD and Arvind are the two grad students who work on this, so I'm really happy to be working with these guys. And my principal collaborators in microbial ecology, Dave Karen, oceanography for Jones, and acoustic communication, Urbashi Mitra. And the cool thing is that USC has just put in a huge proposal to build a new marine institute, which is going to be this building, if all goes well. And this is a deep water dock all around it. And the idea is, this is in the Port of Adelaide, so we have bid to have a 100-year lease on this facility here. And if work goes well, i.e. we get the many millions of dollars needed for it, then hopefully this will come into being. So this is in the planning stages, but we were told that we can tell everybody that it's in the planning stages, at least we're trying to get it to happen. And so if it happens, our hope is that we won't have to go out to Catalina Island to stage. We can stage, and we'll have labs at water's edge, basically, which would be fantastic. So if some of you want to do research in this area, we're hoping someday to have sort of a home for people to come to work and have a sort of visitor program and things like that. Not to mention, ships from NOAA and other places also dock along. So we're excited about this. If it comes into being, we'll be very happy. So anyway, so thanks for having me out. I'm happy to take it.
I'm curious as to why you went for the communication model first instead of the Euclidean distance or something.
Yeah, actually we have it's a good question.
Yeah.
It's a good question. I actually don't know how to do path planning on non-metric graphs. So if I give you a graph and I say planning the shortest path on it, the first thing you need, the only thing you need is a metric in Run A star, right? So we don't do anything fancy, right? Everything else is just icing after that, right? If I don't give you a metric, you can't do that, right? So we have a parallel piece of work on which we don't yet have results on actually doing planning on non-metric graphs. We have some initial ideas on it, but we don't have anything crisp yet. So the hope is that these two lines of work will converge, that we will relax that cost assumption, the Euclidean distance assumption of cost is kind of safe for.
Do you have any early intuition as to what kind of
Yeah.
savings or cost savings?
Yeah, so our first cut at dealing with non-metric graphs is to define a class of graphs that are almost metric. So where the triangle inequality is violated by by some bound, and you get to pick the bound, right? So that's a notion of being almost metric. And under that, we're able to show that we think we have some evidence that there are techniques which can produce optimal paths. If we can do that, then our first step in defining these costs is likely to be some kind of a metric that says it's Euclidean times something, but the times factor is a constant. And so the answer to your question is then how bad can you be? You can be pretty bad, right? Because each link in this plan can be a constant factor of. If the path is of length n, then in the worst case you're n times that factor of, which can be quite big. But we will begin somewhere. I mean, that's likely where we'll begin. We don't quite know how to solve that. It's going to be.
We considered making number of sensors as a parameter and seeing what effect it has.
Yeah, you can. But if you make the number of sensors a parameter, what we want to not lose is the idea that more sensors is not better, right? What these information gain measures capture is that there's some intrinsic quality to the data that makes it interesting. It's not the fact that you visited 16 or 20 that's important, right? It's somehow the fact that the right set produces some information, right? It feels like postponing the problem because then you could ask me, what is a good I function? But we feel like the correct thing to do is to define meaningful information gain measures as opposed to doing sort of arbitrary subset selection, like leave out some sensors. So we haven't really looked at, also, since we're looking at one-shot planning right now, we aren't thinking of these as anytime algorithms, where you say, look, make me a plan with 6 sensors and do it quickly. And then that gives you enough time to make me the plan with the 7th sensor, and I've already executed the first step. So many anytime techniques will have that flavor. But we are not framing it like that, right? We're doing this sort of one-shot thing right now. So maybe there's some room for this later, but it's not something we've considered.
Yeah, just a comment about the model for the data mule. It seems like these probabilistic zones that you have sort of reflect a model where the packet is attempted to be transmitted one time.
Yeah.
And there's some 80 or 90% chance of it being successfully received.
Yeah.
But if instead the sensor was configured to transmit until it received an acknowledgement, then it seems like the cost model would be more of a line interval, the amount of time that you have to spend at a certain probability in order to receive the packet.
Yeah, so I should be a little careful about that. BPSK modulation actually sends repeatedly, and it doesn't stop until you get an ACK. And there's some timeout parameter when it stops, of course. And so the rate parameter R governs how frequently you resend. And so that's exactly the resend rate. So in fact, it does encode that. Right? But the way we model it is we essentially, this model basically says that you get 10 tries to send something until you get an ACK. What's the probability of packet success over 10? So we still model it as a packet success rate. I know what you're getting at, which is if you, there are back-off models that adaptively change how many times to send, those wouldn't fit into what we're doing, right? Those would need some kind of an integral model in them, because there would be some aggregate that you would get out of it. In our models, it's still one shot, but it's not because we send only one packet, it's actually sending many packets.
Well, I'd like to end here today, but if people have more questions, we are here for some more time, so you feel free to, chat with him for some more time. Just thank you once again.